Good evening, folks, and welcome to yet another lecture as part of Module 2. So, I hesitated to even do this lecture because many of this information is covered in a basic stats class, but it also is in your textbook, and I think these foundations are really important. So I figured, why not? Why not take 10 minutes just to refresh your memory of a few things? So measures of central tendency, also known as measures of location, are typically among the first statistics computed for the continuous variables in a new data set. So the main purpose of computing measures of tendency is to give you an idea of what a typical or common value for a given variable might be. So before we begin any project, whether it's in this class or whether we're gathering our own information, we want to consider how the data are distributed. How would we describe a particular data set depending on its distribution? Is it a bell curve or is it not a bell curve? And when data do not follow a normal distribution, what in the world do we do? Do we deal with, say, non-parametric statistical measures? And how are each of these different kind of populations treated statistically, whether parametrically or non-parametrically? So when you hear the word measures of central tendency, it's really just these things that we calculate to look at the center of the data. The mean, of course, is one of the most common, and it can be a challenging number because it's the measure that's most sensitive to any change in value. So, for example, outliers can easily influence a value. Students always ask me about the average or the mean of an exam, and I find that misleading. Let's say an 80% was it's an average on an exam. Well, if somebody gets a 0 on that exam or a really low score, then that value has been skewed towards the negative end by a great deal. So it's a very simple calculation, and many of you have done this many times. Median is most applicable when dealing with skewed data sets. So as a student, I often advocate that we want to use your median grade as opposed to the mean. For example, let's say you've got 15 grades in a class and you did really bad on one of them, and it skews your mean way down low. The median doesn't matter. This is going to be the middle number when they're arranged, and it's a much more typical value for you. And the mode we don't use too often, but just the most frequently observed number in a data set. What we do want to look at, however, is our frequency distribution curves, and we will do that later on. We'll let R teach us how to graph some of this data, and it's typically viewed as a histogram, which is a visual frequency display of each measured variable, and it allows us to visualize the central tendency of the data. And that particular diagram down there would be a pretty normal-looking distribution. So with the distribution curve parameters, we can look at several different components of it. We can look at the mean, or a mu, which describes the location of the distribution heap. We can look at the variance, or sigma, and it takes into account the spread of the distribution curve, the spread around the mean, how much variance there are around the mean. A really large variance means we have a really wide distribution curve. And then we use standard deviation a lot, which is really just the square root of the variance. And when we're looking at a normal distribution, with the mean and standard deviation are common estimates about the spread of the data. The formula for standard deviations there, again, it's really just the square root of the variance. And the important thing to remember is when we have a normal distribution of data, 95% of the data are within 2 standard deviations, almost 98% of the data are within 3 standard deviations of the mean. So here we got histogram shape, and it's a direct representation of the population or data set. So it can have many different characteristics or shapes. It can be normal, such as the diagram on the right. It can be non-normal, and if it's non-normal, is it skewed? Does it have kurtosis? Is it bimodal, meaning it's got 2 modes, or does it just come off and have a plateau? All of these are pretty common in data. Normal distribution, which a lot of biological data is a bell-shaped curve. It's symmetrical, convex, and there's no lingering tail region. Skewed distributions, however, they can be skewed to the right, which is the diagram on the right, we call that positively skewed. The values of the mean and median are greater than the mode. And skewed to the left, which is a diagram on the left, the values of the mean and median are less than the mode. So the direction of skewness, you got to pay attention to the positioning of the lingering tail. A long right tail of the data means that it's right skewed, and a long left tail means that the data are left-tailed or left skewed. And that's why I put them on the screen in that particular manner. Kurtosis are also symmetrical curves, but they're not quite like the normal bell-shaped curves. The tails themselves can be either heavier or lighter than expected. And so we have these two kinds of ways to diverge from normalness. Skewness, which we did under the last slide, and kurtosis, which is the one we're looking at this time. So you can kind of be few outliers outside the mean, and that's called platykurtic, and you can see that in the lower right-hand diagram. But when the tails are heavier and they're more outliers than the normal distribution, we call that leptokurtic. A lot of times in the early part of this course, we're dealing with inferential statistics, and that's using hypothesis testing and statistical significance, and it allows for interpretations from the sample. It tells us whether some sort of interesting phenomena occurring in the data set. So whenever we make these inferential references, we want to know how well does our sample represent the overall population, and whether two samples are different from each other what is our acceptable level of statistical probability. So that inevitably leads us towards hypothesis testing and p-values. And we can, of course, have the null hypothesis where there's no statistical difference or associations found. It's what I call the standard quo. And then we have the alternative hypothesis, which is a statistical difference or an association that's found. And the p-value is caught up in this. And the p-value used all over statistics. It's used from t-test to regression analysis, and everyone knows that you use p-values to determine statistical significance in hypothesis testing. Perhaps later on we'll talk about the trends in statistics and what p-values are or how heavily they're thought of these days. But for the moment, p-values are often used to determine what studies get published and what projects get funded. And despite being so important, the p-value is kind of a slippery concept that people sometimes interpret incorrectly. I want to take a really simple approach, and I love what your textbook does in Chapter 2. P-values evaluate how well the sample data support the devil's advocate argument that the null hypothesis is true. P-values evaluate how well the sample data support the argument that the null hypothesis is true. It measures how compatible your data are with the null hypothesis. How likely is the effect observed in your sample data if the null hypothesis is true? And so kind of strictly speaking, high p-values, your data are likely with the true null. But if we have a really low p-value, your data are unlikely with a true null. So a low p-value suggests that your sample provides enough evidence that you can reject the null hypothesis for the entire population. Now, if we're hypothesis testing, we have errors to worry about. They fall into two basic categories, type 1 and type 2, and they refer to the probability of yielding a false positive or a false negative conclusion. So type 1 errors occur when the null hypothesis is incorrectly rejected. Type 2 is when the null hypothesis fails to be rejected when it should have been. And statistical power kind of helps us with the probability of correctly rejecting a false null hypothesis. The level of significance is important within this as well, and statistical power, let me be more clear on that, it's the probability of correctly rejecting a false null hypothesis. So increasing the statistical power essentially lowers the probability of committing a type 2 error and increases the possibility of detecting changes or relationships within a study. And there are three factors that kind of influence the statistical power. Those are the sample size, the significance criterion, which we call alpha, and the variability. So sample size, larger sample sizes are important. Lower variability from sample to sample is also important when we're trying to determine statistical power. Now, The last thing I want to leave you on is a lot of times we have data that aren't quite normal, but we want to do a statistical test where we require a normal distribution of data in order to meet the criteria of that test. So sometimes we use data transformations that can help help us better suit the situation. So we can do log transformations, square root transformation, arcsine transformations. And we'll look at those in this class, and we'll do some of those. But just remember that understanding the fundamentals of the distribution and error are not only important when looking at raw data, but they're really important when we're deciding which test best benefits, which test best serves the data set that we're looking at. So I'll leave you with that, and I hope this was helpful, and I look forward to seeing you in class. Take care. Bye-bye.